So this is quite strange sitting on my own in this room talking to myself, but I hope you're out there and you're listening and you're going to enjoy this. It's going to be a general introduction to extended defects, particularly dislocations in crystals. So I'm going to start quite general and gradually work my way down into the nano world. So here we go. So just a little introduction about where I'm based. I'm in the west of France at the moment, just south of Brittany. Nantes, it's just on the Loire River on the way to the coast, about half an hour from the coast. And this is our institute. So it's one of the bigger materials research institutes in France. And if you ever want to come to visit, you're very welcome. Nantes has a lot of history, a lot of industrial history, and Jules Verne was based here. So we've got these huge mechanical elephants and other mechanical things, a lot of Breton food. Very nice place. And we organise conferences. For example, Nanotech was 2 or 3 weeks ago, which is an international nanocarbon conference, which again, thank you to Belstein for their support with Nanotech. So, layered materials, I think the best place to start when you're talking about layered materials is with this character, which is graphite. Graphite's probably the most well-known and most well-studied of all the layered materials, and a lot of stuff that happens in graphite you can then translate to other materials very, very easily. So graphite, the name graph comes from drawing, and the history of graphite, the first graphite mines were up in the north of the UK. If you know this area, it's called the Lake District. It's lovely walking in the northeast. And there's graphite mines up there. This is one near to Borrowdale. And this was the first mine in about 1570, I think it was. And they found graphite, and being very pragmatic English blokes, the first thing they found to do with it was to draw on a sheep. So the very first use of graphite was just for marking sheep to say that they belong to you. But in the true history of sort of the model of scientific research, often military research is the next thing that comes out, unfortunately. And they found that if you use graphite, you can make molds, very, very clean molds with very smooth surfaces. So if you graphite line your molds for metal casting, you can make very smooth surfaced spherical structures. So you can make very good cannonballs. There's very good thermal conduction. You end up with very round balls. So they're highly aerodynamic. And as a result, if you're fighting the Spanish and the French, like Queen Elizabeth was at the time, your cannonballs go further than theirs. And so that gives you a significant military advantage. So graphite mines up in the north of England were declared a military, well, not a secret, but they were military defence. They had guards on the mines, and access was prohibited. And I think it was about 1650. The price of graphite was actually higher than that of gold. So it's a very important material. I read, and according to it, there's a pencil museum in the Lake District which says that this is where the phrase "the black market" comes from, because people were sort of surreptitiously trading lumps of graphite and ending up with black hands as a result. So graphite's got a long and industrious history in sort of a range of different materials, and nowadays we use it for all sorts of things. It's particularly used a lot for electrodes, so it's very good for passing high current, so using in things like arc furnaces. You can see the picture here is refractory, so it's, again, this is for making molds and giving you, but one of the areas that's really exploding at the moment is battery research, because you can use it inside the battery as one of the internal electrodes, so graphite-based materials. It's also very good for lubrication, although I'm not going to really talk about that today. And because it's so strong in plane, and I'll talk a little bit more about the strength of the material, but you can use it in composites. So there's a wide range of applications of graphite. And one that's going to come up a bit today is it's also used in a certain class of nuclear reactor. So this is used for neutron moderation. So you make a shield around your uranium core, and when the neutrons come out, the graphite can slow these neutrons down. And so then it's a way of generating more thermal heat, but they get damaged in the process, and the damage process is quite interesting to study. So a wide range of applications for graphite. And this is why we say graphite is layered and is anisotropic. This is the atomic structure of graphite. So the atoms of carbon are arranged in hexagonal planes, sitting one on top of the other. And you can see that they're slightly offset. So we call this A-B stacking. They're not quite on top of each other. They go up in slight wobble. And this is J.D. Bernal, who did the original X-ray studies which found the crystal structure. And it's highly anisotropic, so the bonds between the carbon atoms in the layer are extremely strong. So you can see you've got an elastic modulus of a terapascal that's extremely high. And sort of in principle, if you could make an ideal sheet of graphene, a single layer of graphite, so you wouldn't be able to see it, you could balance a pencil on top of it on this point to put an elephant on top of that and it wouldn't break. I mean, that's a thought experiment. I don't think anybody's actually tried that. But if you look at the outer plane bonds, they're extremely weak. So there is a mild bonding and there's lots of van der Waals forces, but it means that the layers can slide over each other extremely well. So the elastic modulus in the other sense is very low. It's relatively compressible, and you can use it as a lubricant because these layers can slide over each other. And as a result, you have the same for the conductivity, the electrical and the thermal conductivity, that you can pass current very easily in the layers. But if you try and pass current out of the layers, then the conductivity drops enormously. So there's a huge disparity in behavior between these two directions. Now, you don't always see them in bulk graphite samples because they're often polycrystalline. So you have little zones of the crystal oriented differently. And so you have a sort of averaging of properties. But when we start to go down towards the nano world and the nanoscale, where we're looking at much more individual layers and individual crystals, then this anisotropy in properties starts to become very, very important. So now a little diversion. That's the material that we're going to talk about. But I wanted to just, for those people who maybe it's a little while since you've seen this or you've not come across it before, the idea what is a dislocation and what does it do and how is it involved in mechanical deformation. So I stole this video from Tech Science, which is excellent, showing the idea of if you mechanically deform the metal, if you twist the metal, what you're doing, if you're actually doing a ductile behavior, then you're breaking the metal planes. So you're slipping the layers of atoms one over the other in a metal. And so this is a schematic showing that's how it's deforming. So this is what in principle would be happening at the atomic scale. So this is just a simple square lattice, and I'm mechanically deforming, so I'm twisting the lattice over. And as I push it, the bonds have to break, and I end up with this deformation push. So here I push the top and the bottom and slid over each other. So I've had to break a whole plane of atoms, but that's very expensive to do energetically because you've got to break the whole plane in one go. So what materials prefer to do is have something like this, which is called a dislocation. And a dislocation is an extra layer of atoms in the crystal. So now when I push the top to the right and the bottom to the left, instead of having to break all the bonds in one go, the dislocation allows you to just locally break one bond and reform the other. So it's a local deformation, much lower energy barrier, much easier for the material to do. So that's what happens in things like metals. As you start to deform a metal, you start to have dislocations which then drift through the material like this. They glide through the metal, and that's how metal layers can move. It's a little bit like if you take a carpet, whereas if you try and drag the whole carpet, it's quite difficult to do, but if you flip the edge and a little ripple runs through the carpet, then that's relatively easy. So that's the idea of a dislocation. Now, I hope that was not too fast. So this is an example. This is called an edge dislocation. It's to do with the orientation of the dislocation, but there's that little extra bonus plane that we saw before coming into the crystal that's stopping. So in an edge dislocation, you have a layer of material that stops at some point, and then the other layers distort around it. So it's longer at the top than at the bottom, and we have something called a Burgers vector, which is the difference in the distance between here and here. And this is a nice classic 2D square lattice. So can you see edge dislocations in graphite? And the answer is yes, you can. And this is right back in some of the early days of some of the earliest microscopy. So you can only just about pick out, these are the individual layers of graphite that we saw in the image before, and they've been counted, and you can see that there's layer number 4 over here is missing. So you can just about see with a practiced eye, these two layers here come together and sort of merge at this point here and then carry on. So this is the dislocation oriented like this. So this was John Robertson's colleagues. So dislocation is actually quite common in graphitic materials like this. And if we look at the structure, we can start to go down and see how the atoms are arranged in the kind of core of this dislocation. So this is the missing plane, the plane where we've cut it off. So we've got to cut through our graphene sheet, through our sheet of hexagons, and we've got a choice about the orientation that we cut. So this is looking down on top of the sheet now, and we can cut along in the most basic configurations these two lines, the red or the blue. And if we cut along the red line, this is the 2 bar 1 bar 1 0 in terms of crystallographic symmetry, then you can see that if you take off all the right hand side of here, you're left with this zigzag edge. So that would be the edge of our extra plane sticking to the graphene. If we cut along this direction instead, then it gets called the boat or the armchair edge. if you've got a very good imagination, you can imagine these 4 atoms a little bit like a little seat, with these being the arms of the armchair. I think that's why people call it armchair. Actually, you need a very good imagination, but that's an armchair edge. So we can cut in those 2 directions, or we can cut with something in between the 2. And depending how we cut, then the center of the dislocation behaves differently. So this is an armchair edge. So this is the one where it was going up and down in crenellations and steps, like the top of a castle. And the edge, when you relax it in a quantum chemical calculation, this is a density functional calculation, the edge just sits there. And if we zoom in, the way it works is right down here. If I now look along the edge, so we're looking along the line, if you look at the bond lengths, then the atoms form very tightly bound pairs. So this is almost a carbon-carbon triple bond. So it's rehybridized and stabilized the edge. So you've got a nice, relatively stable edge that just sits and stops in the graphene, in the graphite. And the bond length is triple. If you cut in a zigzag direction, it's not quite the same story, because the zigzag direction is quite reactive, it's quite unstable. So what does it do? Instead of just sitting there on its own, to try and make itself more stable, it bonds into the neighboring layer. And these atoms here end up with an extra chemical bond, and they become over-coordinated. So if we zoom in, you can see that all these atoms here have all got, well, they've got 3 neighbors continuing off into the sheet. And along the core, you end up with these atoms which are 4-fold coordinated. So this becomes what we call sp3 coordinated. So right along the middle of the dislocation, they're actually more like diamond than graphene, and it breaks the conductivity of the layer. So by doing this, it stabilizes itself, this half plane, but it damages the plane next to it. And the way it can then migrate is it can then break the bonds, and this layer can pop over and bond into the next layer, and that's how it will move through the crystal. So we have these 2 types of edge dislocation, prismatic edge, and you can see them. Often when people want to see things in graphite in the electron microscope, it's difficult if you want to look side on, because it makes the material very thick. So an easier way to look side on onto graphite is to pick a carbon nanotube. So this is actually a multi-wall tube. So each one of these pairs of layers is a tube inside a tube inside another tube. So that's sort of 10 or 15 tubes inside each other. And you can see that it's in projection, a bit like an X-ray picture of your bones. You can see the layers of the tube where they come up, and you can see these defects here in the tube side wall. So this is in boron nitride, which is the nanomaterial, kind of analogous to carbon. This is inside a carbon nanotube. You can see that as they've been watching, the dislocation has moved from here, and it's managed to move all the way up to here, and eventually it's popped out of the crystal. So they can see in real time, the dislocation is migrating through the wall of the nanotube. So this is where it gets fun, when you start playing with topology in space and such like. So this is the picture we have, the 2D square. This is the picture people always draw of dislocations. And I said I've got an extra plane that stops. Well, the way we built it is we were putting an extra sheet of graphene in and cutting it. But there's no reason that these planes here have to correspond to the actual planes of graphite. We've got 3 directions in the graphite crystal. So this is just, we're talking about an additional layer or an initial row of carbon atoms inserted into the lattice. And we could insert it this direction, but we could also, for example, insert it this direction. So this is the extra inserted material, but the graphite sheets themselves are perpendicular to that. And this is a totally different type of dislocation, because now we're inserting extra material into these graphene planes and not into this plane. And we can even go further, and we can flip it around. So now if we're looking down on top, we're inserting extra material into the graphene plane itself. And because graphene and the graphene layers are so anisotropic, so different in these different orientations, we end up with totally different types of dislocation behavior in these 3 cases. I haven't got enough time really today. I'll see what time we get at the end, but I don't really have much time to talk about the right-hand one, but I'm going to explore a little bit more what a dislocation looks like when you orientate this direction in the crystal. So this is the idea. These are our notional planes. So this is the extra plane of atoms that we've stuck into the crystal. But this time, the actual graphene planes are at 90 degrees to that. So they're very slightly here. So these planes at the top are going to be longer. They've got slightly more carbon material than these planes at the bottom. So in a conventional picture, you'd imagine like this, that you stretch these layers a little bit until you end up something back to normal. But that doesn't really work in reality because, like, as we've already said, stretching graphene plates is really difficult. They have a modulus of about 1 terapascal. You can stick an elephant with a pencil on top. They're very, very resistive. So stretching graphite is something that you can't really do. You're really got to avoid if you can. But what we have is, because this is a layered structure, we have another dimension to play with. And it's one of the fun things with 2D materials, that you can move into 3D space. They don't have to stay flat. So instead of stretching these bottom layers, what you can do instead is start to buckle these top layers. So they start to become no longer flat, but they start to ondulate up and down. So that's what a dislocation, basal dislocation, looks like. And rather than stretching layers, it actually involves buckling up and folding other layers. And this is a calculation where we've done that. So this is actually an array of dislocation. Each little T shape here is a symbol for dislocation. So this is a layer that's got more carbon in than this one, and as you can see, it's flipped up and down. And the size of the space of them here is controlled by the calculation, because we decided how many atoms, extra atoms, to put in, and we don't allow it to spread out because it's periodic. But in real material, in real graphite, they won't be as dense as this. But you can see this changes quite a lot. If this is graphite and you start doing this, this is nothing like that picture I showed you before of graphite with these nice flat layers, each one spaced by 3.35 angstroms. Instead, we've got these big voids starting to form. So the material, as you're putting extra material in and compressing, these layers are being pulled in, and the expansion in this direction is quite dramatic. So the whole material is getting fatter. So your material starts to change in dimension as you put tight dislocations in. And that can have important implications. So first question, how can we push? So you saw my picture at the beginning where I was saying the crystal was sliding with the dislocation when you're mechanically deforming. So how can we deform this graphite in order to introduce these dislocations? Well, this is one way you can do it. This is a zoom in on a graphite reactor. So this is a nuclear reactor, and these holes are where the uranium rods go into the reactor. And this is what the cores look like, made out of graphite. And these are being irradiated by these neutrons. And what they'll do is kick out some carbon atoms just by a very small probability, which are then traveling very fast. They then kick into other atoms and start knocking those out. Those knock into, and you get tertiary knock-on. So all the atoms start to get this kind of scattering of atoms all smashing into each other inside the graphite. So there's a lot of impact. So it's a little bit like on the atomic scale, you're distorting the material. So it's fine. You can imagine these impacts coming at an angle, and there'll be transfer of momentum. So some of the atoms will be flying out straight, but some of the momentum of that impact will be transferred to the sheet. So you're going to start sliding the sheet and pushing it along. And what does that do? That makes these dislocations, it makes these ripples. And if you have a lot of them, if you start to run the ripples into each other, one after the other, then the fold becomes bigger and bigger until eventually it hits a sort of a tipping point when suddenly it's more favorable for the whole thing to flop over and make what's called a ruck and tuck defect, which was first discovered by this guy, Malcolm Heggie, down in Sussex University. And it's where the graphene actually the layers start to fold back on themselves and double over. And you can see this as either a pileup of Klein dipoles, dislocation dipoles, or indeed as an unfolded Klein dipole in a different direction. It's just a sort of nomenclature issue with dislocations. So as you start to smack your layers of graphene, they start to fold over and you get these ruck and tucks. So again, you can see that the graphite is expanding in one direction, shrinking in the other. And can you see them in reality? Well, you can. This is some lovely work by Steve Johns and his colleagues, where not many people like doing this because they've been irradiating nuclear graphite, cooking it at 800 degrees C, and then sticking it in their electron microscope. And people don't generally like irradiated materials in their microscopes. So there's not many studies doing this, but you can see these S-shaped structures coming up. And this is probably the best. It's really nice and clear. And this is where momentum's been transferred to the layers. They folded over and the whole thing's expanded. And you can see what it's doing to the graphite. It's pushing the layers out and expanding it. And this is actually a big issue. So this is from a kind of like the Bible for carbon scientists. Is a book by a guy called Brian Kelly on the physics of graphite, because a lot of the early graphite work came from the nuclear industry. And here they're looking, as you increase the dose of neutrons at different temperatures, how the material expands in the C-axis. Now, normal, when I say sort of standard materials, you get expansion in the C-axis, but it's not significant. Here you're getting massive expansion in the c-axis. So this is sort of orders of magnitude as a percentage. Well, it's going up by over 100% sometimes. This is at lower temperature when the dislocations are locked in by other defects, and this is at higher temperature when they start to make these ruck and tuck ripples. But you can still see that the c-axis is expanding a lot, and at the same time, this is the a-axis, so the material is contracting in the other direction. And what that means is if you've got a large polycrystalline material, each crystal will start to shrink in one direction and expand in the other. And if they're all in different orientations, you can imagine your polycrystalline material will gradually start to fall apart and crumble. And this is actually a life-limiting factor on nuclear reactors using graphite moderators. So some of the UK reactors are coming to the end of their life, and this is a really important factor in controlling the life of the reactors, is how the graphite crumbles. So that's one way you can introduce folds, but there's lots of others. One is the nanoworld. So now we're peeling off layers of graphite and calling it graphene and studying these individually. And one way you can do it is something called shear mixing. So this is essentially putting lumps of graphite in soapy water in a food blender. You can actually do that. It's an experiment that's been published. And the shear mixing, as the blades go round and they put shear forces in the fluid, it peels layers off the graphene, and you can make very nice individual layers of graphene, but they are naturally quite often crumpled and folded. It's just like very floppy paper. It's very hard to pull, but it's very easy to fold up. So often shear mixed graphene will have folds in it. You can do it by dual heating. If you've got lots of edges of your graphene and there's no hydrogen or oxygen on the edge, so all the kind of dangling bonds of the carbon are sticking out, if you heat it, then they'll bond together into pairs of layers to avoid these dangling bonds. So you can end up with these sort of loops on the end of graphite sheets, but also on the end of carbon nanotubes that have been annealed or other carbon nanomaterials. So you get folds in quite a few different situations. And this is one I just wanted to focus on a little bit. This is forming folds by collapsing carbon nanotubes. This is a lovely picture by Marcel Motta when he was working in Cambridge, and they've got a flow reactor, so they can produce nanotubes continuously, a little bit like the way you make, in French it's called Baba Papa, the candy floss. So you can produce these as like a smoke of nanotubes that you can pull out of your reactor in a continuous way. And you can see that most of these are large, well, not in this picture, they're normally large double-walled nanotubes like this, so it's a tube. But if they get too big, then they start to become collapsed like this. So the cross-section of the tube is no longer circular, and instead you've got these little folds at the edge. And there's different ways you can collapse nanotubes. Either you can twist them. So this is a student who was doing some work with me on this. It's just like pipes. If you twist a pipe, it collapses. You can squash them. So you can do this in diamond anvil cells. You can take nanotube bundles and literally crush them, and they'll start to do this. But I'm going to focus on using thermodynamics. So the idea here is you just go for big tubes. And the logic is, if like you imagine a big rubber tube, eventually it'll collapse, and that's gravity doing it for you. In this case, it's collapsing because you've got van der Waals interlayer interaction between the two layers, which is quite weak. So if it collapses, it costs more energy to have these sharp curved edges at the edge. So that's costing you energy at the edge, but you're gaining because of this interlayer interaction. So there's a competition between the two processes. And as you make your tube bigger and bigger, the curvature energy is fixed because there's just always two curves at the edge, but the interlayer energy increases as you increase the overlap. So basically, as your tube gets bigger and bigger, this term will get bigger and bigger until eventually it's the dominant term and the tube will collapse. And that's what this plot shows by Hay and colleagues, where this is the collapsed tube. So for small tubes, it's more expensive to make, that the energy is higher than for a rounded tube. But as you make the tubes bigger and bigger and bigger, you reach a threshold, which is about 5 nanometers. And above that, it's more stable to make collapsed. So what this says is that under normal circumstances for clean single-walled carbon nanotubes, you shouldn't be able to make them bigger than this, because if they're any bigger than that, they'll all be collapsed. And they'll look like this. But the good news is these are interesting, so it doesn't really matter. We can do some nice stuff with these. And this is another way to make them, and this is some work that we did in a collaboration with Bordeaux and with Toulouse, is you can take these large multi-wall tubes, which are much, much bigger than single-wall tubes, and you get them from an electric arc, so they're nice and clean, and then you use an extraction process, you use surfactants and treat them in such a way that you slide off the exterior tube, So it comes off as a single tube, and now it's way bigger than your threshold, and so it spontaneously collapses. And this is a way that we can make experimentally flattened carbon nanotubes. And this is an example where they did it, diluted them, and dropped them on a silica surface. And this is using an AFM microscope, so measuring the size of them. And you can see that these are different ones here, different tubes. Where it's marked CNT, then they're quite high. So these are still carbon nanotubes where they haven't separated. And where it's marked FCNT, these are ones which are flattened. So they've managed to slide off the surface and crush them down. So now we've got a map of these on the surface, we know where they are. We can now look at each one of these individually and see if we can work out some sort of spectroscopic signature of these folds. So something that we can measure and identify the presence of folds. And if we use Raman spectroscopy, so this is looking at vibrational spectroscopy, looking at the vibration of carbon-carbon bonds, and you can see for the cylindrical tubes, you have a very classical Raman spectra for carbon material. So this is called the G band that comes out very nice cleanly, and this is called the 2D band over here. And there's nothing over here, so these are nice clean tubes. So that's exactly what you'd expect for a carbon multiple carbon, nice clean multiple carbon nanotube. But when you scan the flattened ones, then you see suddenly this huge peak here appears here called the D band. And it's called the D band because people normally associate this with damage or defects. So it's a signature of defects, and there's a bit of a splitting in the G band as well. So these have a very characteristic signal that's quite different to their original host carbon nanotubes. And you can understand what's going on here by doing some calculations, which is what we did. If you look at this, is called the phonon band structure. So these lines are maps of the vibrational modes of the different atoms in a sheet. And up here at 1600 wave numbers, this is this G band that I showed you. So this is this peak here. And it's the carbon-carbon bonds stretching. So it's all the bonds collectively moving in and out. And this is our calculated spectrum, and that's these peaks here, these bands here at around 1500. So you can see in our collapsed nanotube. So I'm looking down on top of the nanotube now, and this is the fold along the top. And you can see it's the carbon-carbon bonds stretching. It's split a little bit because now we've got asymmetry. If they're vibrating towards the edge of the collapse or vibrating along the axis, then they're not quite the same frequency. But then we've also now got this peak, and this is a whole hexagons breathing in and out. And this is called the D band. Now, normally this isn't allowed because this involves along, I haven't got time to explain a phonon band structure here, but this involves a momentum change. So going from anything on this energy line to this energy line, you have to transfer momentum to get across there. And you can't normally do that. That's not allowed by symmetry. So what's happening in this case is that the edge is breaking the symmetry. So your perfect graphene sheet or your nice round nanotube won't have this mode because it's too symmetric. But by putting an edge in, you break the symmetry, and this mode now folds onto the gamma point, and so you can see it. So you're not actually sort of damaging the nanotube in the sense of kind of putting defects in it, like point defects. You're only damaging it by breaking the symmetry, but that's enough. As soon as you fold it, then this peak comes up very, very strongly in the measure, in the calculations. So something you should be aware of if you're working in graphene and, for example, you're separating sheets out and your separated sheets have a big D peak, it might not be that they're riddled with damage and your method is very poor. It might just be that they're very crumpled up, so they have a lot of folds. It's basically, if the D peak is intense and very sharp, that's probably what's going on. So it's probably good news for people developing new ways of making graphene sheets. So how else can we impart momentum? And I'm going to have to accelerate a little bit. Another way you can do it is by thermal contraction. So you know that if you heat up a material and then you shrink it, then all the atoms start to move in and all the bonds shorten. And that can stress a material depending on the shape. So that's another way to put stress in and in principle induce folds and ripples and dislocations. Now graphite, normally you'd think this isn't important because if you look at the thermal expansion coefficient, so this is how much the layers change within the layer as you heat up, it's almost zero. So basically the space between the carbon atoms at room temperature is almost identical to the space between the carbon atoms at about 3000 Kelvin. There's very, very little expansion. But if you look out of plane, there's actually quite a significant expansion. So this is early data from back in the 50s, where you look at the increase in temperature here in degrees C, and this is the space between the layers. It increases reasonably significantly. Now, when you're making graphite, that doesn't really matter because you've got all your layers, and as you cool down, the layers just contract and the whole thing just sort of shrinks down a little bit. But what happens when you've got a multi-walled nanotube? So in this case, if you're using something like an electric arc to make the nanotube, you're heating to about 3,500 Kelvin, extremely hot. So at equilibrium at that temperature, the layer spacing is about 3.8 angstroms. So it's actually 13% bigger than it would be. So your tube, if it's growing in equilibrium conditions at this temperature, wants to have a layer spacing of about 3.8. That's fine, it can do that. But now when you cool down again, the atoms can't go anywhere, they're stuck in the layer. And now they want to be at 3.3 angstroms, so they want to be a lot closer. And it's got to somehow retract. So I could give you 30 seconds with a pen and a piece of paper and you can sketch this out and see if you can work out what it's going to do. But the answer is it breaks symmetry and you get a bulge. So this is what we get from our calculation. So the interlayer spacing is now dropped when you've gone back to room temperature and it's cooled down. But as a result, they don't fit perfectly. You end up getting a little local bulge. So is this just theory? And the answer is no, it's not. Here's pictures of arc electric nanotubes. And you can see, for example, if we take this bottom one, you've got nice layer spacing on one side, and on the other side, you've got these little rows of gaps. And this is from an early paper by Huang, which shows the same effect. If you take a large system, then the bulges tend to line up one with the other because it makes more sense mechanically. So you get all these extra little gaps on the same side of the nanotube each time. And this is actually very common in really nice clean arc electric nanotubes. So if anybody tells you that a multi-walled nanotube is cylinders inside cylinders, the actual answer is not quite. If they're high enough temperature, then this is the case that they distort. If you grow them by other methods, which are lower temperature, then this won't happen because the layer spacing change isn't so significant. So how can we prove that these little holes, well, we can do something with them. So that brings me to the next bit of the talk, which is okay, we've talked about folding and twisting and holes. Why? Why is this interesting? What can we do? And the first question is, can we put something in them? So this is a little test. Unfortunately, we can't do this, but we can use things like iodine. So this is an example where some colleagues took these multi-walled nanotubes, the one you saw before, and you open the ends of the tubes and you just put a gas of iodine and the iodine goes into the tubes, except it doesn't. You can see here that the interior of the tube, there's no iodine. This is the two walls. But you can see these bright lines, and this because it's a dark field image, the bright lines correspond to iodine atoms. And if we zoom right in, you can actually just about see the individual dots, which is the individual atoms of iodine. And they're making these lovely lines. And the first thing you can see is that they're always just on the same side of the nanotube. Here we've got 4, so they correspond to the gaps that we saw, and we've actually done corresponding bright field images to confirm this is the case. So because the layers are buckled, there's just enough space for iodine atoms to fit in there, just one at a time in a row. And they're very stable there because they transfer charge to the surrounding sheet, so they sort of sit in a little cocoon of charged carbon. So you make little cavities that you can fill. So this is, next question is, okay, if we can do that with those kind of buckled multi-walled tubes, can we do it with these collapsed tubes? Can we start to put something in here, in the ends? And we were interested in this because we thought, well, this gives us like a ribbon of graphene, if you imagine it going into the screen, and then we can put something in here that maybe can dope this and transfer electrons and make it like a very conductive ribbon, for example. And one of the things that's nice with this is if we put something in here that interacts strongly with the carbon, then we can change this curvature energy. So if we put something like iodine in the center of that, it should stabilize those curves, those kind of edges. And this is an example. We think that's what we have. We haven't got confirmation because this was very difficult to do. But this, we think, is a collapsed tube with 2 lines of iodine. And the size of that, the radius of that, is too small. So we wouldn't expect a tube of that size to be collapsed if there was no iodine present. But if we do the calculations again, so we compare the cost of this curvature energy against the energy gain of the interlayer energy, by stabilizing these, we make the cost less. So it's easier to collapse into these tight ends. And so that means that the interlayer energy wins earlier. So that means you can collapse tubes when they're smaller. So this is the difference in energy. If you're on the top half of this graph, above the dotted line, it's more stable as a tube. If you're on the bottom half, it's more stable as a collapsed structure. And this is when there's no iodine. Here we're cutting at about 4 nanometers for this level of approximation in the calculation. And as soon as you put iodine in, you're collapsing down at about 3 nanometers. So iodine is actually stabilizing these. So it's quite nice. It means that you can, in principle, have a system of nanotubes. You put something in which goes into the tube and they will collapse. So you have a mechanical response to intercalation. And there's other things that can also help you with collapse. If you're next to a surface, then that stabilizes. Again, that increases the interlayer energy here, so that will also help them collapse. If tubes are together in bundles, that will also do it. And if you shift the Fermi level, this was a calculation that Anthony did. So if you start charging the nanotubes, so if you, for example, you put an electrode in and charge all your nanotubes, then if you charge them in the right direction, then you can change the cutoff. So you can either pop them open or shrink them down in principle, which could be made very nice for mechanical actuation or electroactivation. So if we can put iodine into these edges, can we put anything else? And this is another difference with carbon nanotubes, because you may have seen those working in nano, where people have filled carbon nanotubes with molecules and such like. One of the nice things with folds is that they can vary in size in a way, so you can change the diameter in a way that you cannot with a nanotube. So this is 3 examples where groups actually put C60, put fullerene molecules, so football-shaped molecules, into the fold. And you can see from our calculations that the fold is now much bigger, because it can simply expand and contract to match the size of the intercalated molecule. So that's really nice. You can, in principle, use that in a way that you couldn't do with a carbon nanotube, which would be fixed. So you can have a lot of fun playing with cavity size. This is, I have to say, much harder than it maybe looks. So there's a lot of clever materials treatment that you need to do in order to make your samples clean enough and well treated to produce images like this. So it's not something that's easily scalable yet, but you can still do very nice science with it. So just a little bit about what we can do with folds. This is when you take a sheet of graphene and you roll it up. If you roll it into a carbon nanotube, then the electronic properties are very different depending on the direction that you roll it. When you grab the sheet, you can roll from this side to this, or you could roll from the top to the bottom. And if you do that, you end up with 2 nanotubes with very different, one could be metallic and one could be semiconducting, for example. So the rolling direction is something you call the chiral vector, and that determines the electronic properties. So that's carbon nanotubes. But once you go to folds, you've got an additional play. So you've got the direction that you folded the sheet, but then you can also slide the layers over each other, a bit like an attractor mechanism. So that allows you to change the stacking by shearing the layers, and it can stabilize itself by shearing the layers forwards or backwards. And that has a very strong, can have a very strong effect on the behavior of the material. So if you do this in graphite, so this is a sheet of graphene we folded over, the energy difference is very, very small, and it doesn't change the electronic properties. It does, but not much. So instead, I'm going to switch materials and talk about another material a bit like graphene. It's called boron nitride. So each one of these corners is an atom, and it was carbon. Now it's going to be boron, then nitrogen, boron, then nitrogen, alternating. And this is boron nitride. And unlike graphene, this is a material which has a very wide gap. So this is a strong insulating material, and it ideally likes to be in this AA prime stacking. So alternate layers on top of each other have a boron above a nitrogen, above a boron, above a nitrogen, because they're highly charged, positive and negative. So they like to stack in alternation. And if you fold along the 1, 0 bar 1, 0 direction, you can shear your graphene layers. And this is a map where we've done that in the calculation. So this is just 2 layers, not with a fold, 2 infinite layers, and we just start to slide them around on top of each other. And as you slide them around, this is where we've calculated the energy gap. So this is how insulating it is. And this is the ideal case. This is the AA prime up here. But as we slide the 2 layers over each other, you can see that the gap drops, and you can change it by up to 1 electron volt. So it's quite significant. So as the layers start to slide over each other, the electrical properties will change really significantly. And there's other examples, for example, when you do twisting and you do wiring patterns, which mean that locally the band gap of the boron nitride could vary very significantly. If we do it in the other direction, the zigzag direction this time, so now you can see along the edge the atoms are zigzag. And one of the peculiarities about a fold in this direction is that you can't build AA prime anymore here. You can't stack every boron above every nitrogen. It's just not geometrically possible. The best you can do is this AB3 type structure. So they're close to it, but they're not quite stacked. So again, it means that the band gap is way off your AA prime band gap. So you can really control you really end up with quite different electronic properties in the material that's folded this way. And as a result, a zigzag fold is more energetically expensive than an armchair fold. So we think from the calculations that if you fold boron nitride, there should be like preferential directions of the folds in the crystal. And we've got preliminary microscopy data supporting that idea, but it's not confirmed yet. Now I'm going to really accelerate because I'm going to run out of question times. And the other thing about the boron nitride is that you get electronic states which localize around the fold. So this is states that sit inside the band gap. So basically the electrons can be trapped locally at the fold. So these can act as electron traps, and they can also act then for light emission or light absorbing, for example, like a little quantum junction. So this is really just about me done. I just wanted to say that I focused on these sort of dislocations where we're putting them into layer and we're getting these wrinkles and folds and twists and filling these. But you can do the same with these. So these going right back to the prismatic dislocations that we saw at the beginning, which graphite is full of, or can be full of if you make the graphite right. Can we fill these in the same way that I was filling the folded sheets? And our preliminary calculations, again, this is a calibration with Loughborough, look like you can. So this is bulk graphite. And graphite is used as an electrode in lithium-ion batteries. And below this line is energetically stable. And this is the concentration. So as you go to the left, your concentration of metal is increasing. So down here, lithium is very stable, pushed in between the layers of the graphite. So that when you charge a battery, that's what you're doing. You're pushing the lithium in between the layers of the graphite, and the graphite's expanding. So lithium likes to do that. Sodium here is endothermic, so it's above the line. So sodium doesn't like to go between the graphite layers, and that's the reason that it's very difficult to make sodium-ion batteries, at least with graphite electrodes, much as we'd like to. And potassium does under certain concentrations. So lithium, okay between the layers, sodium not. But if we put a dislocation in, then locally the material is very low density. So there's more space in the lattice. And if we do calculations for that, we find that the sodium actually is stable along the core. So it looks like you can actually put sodium into graphite materials if there's dislocation. So if we can control the dislocation density and behavior and type, then this might be a route towards us using it to make better battery materials, for example. Anyway, that's all I wanted to say. It was just a very broad flyover, folding and twisting and bonding of layers and dislocations. So I wanted to quickly thank the colleagues who did a lot of calculations, like Dimitri and Anthony, particularly with Anthony was his PhD, Dimitri and postdoc, and various other experimental and theoretical. And I just wanted to briefly mention this chap, Malcolm Heggie, who was my former postdoc supervisor for many years, a mentor and a bit of a guru on all things dislocations, and unfortunately no longer with us, but a great character and a real motivation for lots of this work. And thank you all for listening. And thank you, Belstein, for the invitation.